So let's assume that we have a data set D, which is a set of n data points or n observations, xi and yi, or I goes from 1 to n. And let's assume that the yi's are generated using a function which is parameterized by the parameter w and the basis function, plus some noise, epsilon I. So this epsilon I here denotes some random noise in the data. And we assume that this random noise has a mean as 0. So the expected value of epsilon I is 0. So this epsilon I is a 0 mean random noise. Right. What does it mean actually? So let's consider a small a sample data set. So this is our x-axis and this is our y-axis. So let's assume that y is generated by some function x square. Right. So ideally you would have a perfect, if this was the case, right, and let's assume you have a perfect data, right, which has no noise. I'm just drawing it approximately, so don't worry much about the accuracy of this plot. So let's assume we have a perfect data set, right? So in that case, we can definitely fit a function. If we fit this model, let's suppose we try to fit y equal to w1 times x square plus w2 times x plus w3. So perhaps you will find that w2 goes to 0 and w3 goes to 0 and perhaps w1 would be 1. That would be the optimal solution if the data is perfect, right? But typically what happens, so this is an example of a perfect data set, right? But often in real world, data is not always so perfect. There's always a noise in a data set. So if you consider this as data set, so this data set is still generated by the function y equal to x square plus some random noise. So we can still fit the function. Perhaps it will look something like this. Right. It's still a quartic function, right? But there would be some error, right? For some of the data points. For example, if you consider this particular data point, it will have some error. Right? So in that case, once you minimize the loss function, it will never be 0, right? If we fit a function like if our f of w is w1 x square plus w2 x plus w3, in this case, if we try to fit this function, the error you can check it, like it will never be 0, right? There's always some error because there's some random noise in the data set, right? So this will incur, this point will, even after you fit, even if you could compute the optimal parameters, will still incur some noise when you feed all these points in the loss function, right? To give you a better, like often real world, there's always some noise in the data, and often that noise is a random noise, right? To give you an example, or a realistic example, right? Let's consider that your goal is to, we haven't still covered the classification, but let's suppose your goal is to classify every pixel in an image, right? So let's suppose you have an image. This is your image I with some m rows and n columns, right? And let's suppose your goal is to classify, so there would be like m cross n pixels in this image, right? Now your goal is to classify, let's suppose for each of the pixels, you want to determine whether this pixel is an obstacle or environment. That is, this pixel belongs to obstacle, belongs to some obstacle, or belongs to the generic environment in an image, right? So what you will do, we haven't covered the classification, but for the sake of simplicity, let's assume that it can be solved by regression, right? So here we will feed, we will have lots and lots of images to feed to our model, right, that we want to train, right? So what we'll do, right, in each of the images, let's suppose we get a human being to label the images, right? So I suppose there is a vehicle in the image, right? And we get, we are labeling each of the labels. Some human being is labeling each of the pixels in the image, right? So perhaps, like let's suppose we provide them a software that they can use to draw a bounding box around the vehicle. So perhaps they will draw a bounding box like this, right, with some 1 or 2 pixel error, right? Sorry, it looks more, but this is just 1 or 2 pixels gap. So perhaps they will label something like this. So for most of the pixels inside the bounding box, inside the vehicle, they would have accurately labeled it, right? Inside the bounding box, every pixel belongs to vehicle. But towards the very edge, right, it's very hard to label it very precisely. They can miss 1 pixel or 2 pixel, but through no fault of their own, right? It's just the data set is like we are semantically labeling the images. We are drawing a bounding box around the vehicle, and it's very easy for a human being to miss 1 or 2 pixels. So some human beings may error perhaps over here. They may draw a boundary inside the vehicle missing 1 pixel at the edge, which should have belonged to obstacle, but they wrongly labeled it as environment. In some cases, a pixel may be belonging to environment. They might have wrongly labeled it as a vehicle, but they did intentionally labeled it wrong, right? So let's assume if we have 1 billion images, right, and we have lots and lots of human power to label those images. So every human being will label it independently, and they may incur some error, 1 pixel here and there near the edge, right? So you can see that the noise is an artifact here of a human labeling, right? Through no fault of their own, they just made some error, but that error is random. Sometimes they may wrongly label a pixel as obstacle. Sometimes they may wrongly label the pixel as environment. But overall, it would be balanced, right? They are not intentionally marking, okay, let's go beyond the obstacle, or like let's cross the boundary of the obstacle, right? So this is one example where the noise in the data set is generated, and often most of the data sets in real world have noises. Even when you capture images from a camera, they have some noise, and every signal has some noise, every sensor has some noise. So every data set that we collect in real world has some noise, and that's why we assume that the yi is generated by some function plus some noise. So as we have seen, that often in real world there's always some noise, right? So let's assume in our case that the target values yi are generated by some function of phi of xi plus some random noise epsilon I. Right. Currently we are not assuming that this is linear, because it doesn't make any difference to our discussion that we're going to have. So let's not assume that this is this function is any special class of models. So let's assume that this is a function which takes an input the phi of xi and it generates the target value yx. Right. So given this model, and we are going to assume, currently we're just assuming that each of these epsilon I are zero mean, they have zero mean, and each of the epsilon I is independent of epsilon j for I not equal to j. So epsilon I is independent of epsilon j for I not equal to j, which means that the covariance of epsilon I and epsilon j is equal to 0. We also assume that the epsilon i's are independent and identically distributed. What is IID? What is independent and identically distributed? Simply the IID mean, right? So let's assume we have a sequence of data points x1 to xn, right? If these data points are IID, let's assume that they are drawn from a distribution function P, probability distribution function P. Then also, like, what does it mean for them to have independent identical distribution? So what it means is that probability of x1 given x2 is just probability of x1. That is, the probability of observing x1 is independent of the observation x2. And likewise, we can also write like probability of x2 given x1 is just probability of x2. Right. This also means that the joint distribution, joint probability x1, x2 is simply p of x1 times p of x2. So if these samples are drawn IID from the distribution P, then it means that they are independent, that the probability of observing x2 or any xi is independent of the observation xj for I not equal to j. Right. So we can erase all this. So we have assumed that yi is some function fw of phi of xi plus some random noise epsilon I. So what is the probability of observing yi given some xi, and the function which is parameterized by the parameter w? What is the probability of yi? So the probability of yi is simply probability of epsilon I. Right. So, sorry. probability of yi given xi and parameterized by w is simply the probability of epsilon I. Now, how do we understand it physically as to what is happening, right? What's the intuition like? How did he arrive at this particular? Although mathematically this is correct, but can we understand it more intuitively? So let's begin with understanding what it actually means. Like, what does probability of yi given xi and the parameterization parameters w is equal to probability of epsilon I actually mean? What does it mean? Right. So we are just going to write it again. Probability of yi given xi and the parameterization parameters w is simply probability of epsilon I, where yi is some functional mapping fw of xi plus some random noise epsilon I, where our assumption on epsilon I is that it has mean 0, epsilon I is 0, as well as each of the epsilon i's are IID. So what does it mean? So let's consider this equation again. Let's assume that there's a function like fw of phi of xi. I should have written phi over here. Phi of xi. Phi of xi is generating yi, right? And there is no noise in the data set, right? That is, for each of the xi, given the xi, fw can perfectly generate the target values yi, and there is no noise in it. So the epsilon I in this every case, the epsilon I is just 0, right? So in that case, if the function f perfectly explains the target value, the target observation, so in that case, what is the probability of yi given that we observe xi and we have been given the parameterization parameter w? In that case, the probability of the observation yi is 1, given that the w is the optimal parameter. If w is not the optimal or the true parameter of the function that generates this data, then the probability of the observation yi given xi parameterized by w is simply 0, right? Because we are assuming that there is no noise in the data set, and we have somehow learned the true functional mapping, right? A true function with parameterization parameter w, right? So if we can learn the true optimal value of w, in that case, whenever we feed in x, we'll get the output y, right? With no noise, right? So in that case, if w star is optimal, if w is optimal, w star, then the probability of yi given xi parameter w is 1. If we don't have the optimal parameter, w is not equal to w star, then in that case, when you feed w, which is not equal to w star, phi of xi, it just generates some value, y hat, which is not equal to y hat, right? So assuming that we have no noise in the data, and we have access to the true function, the true functional mapping, right? It can be linear, it can be nonlinear function, and it's parameterized by W. And with the access to the true parameters, in that case, the probability of observing yi given xi. So we have a data, the input data sample is xi. We observed it, parameterized by W. So given the xi, yi will have a unique value. So p of yi, in that case, just 1. If it is equal to fw of phi of xi. Right. But in case of a noise, if we have some noise in the data, so in that case, yi minus fw of xi is, sorry, 5, I should mention phi of xi. Is epsilon I, right? So again, let's fix w equal to w star. That is, we have access to the true function that generates the data, and also we have access to its true parameters w star. So in that case, and we assume that the dataset has some noise. So in that case, the deviation from this, let's suppose this deviation is lambda, right? So you plug in the xi into this function, right? You plug in xi into phi and you feed the resultant vector into the function fw. It will generate some value y hat, right? And the observed value is yi, right? So the discrepancy in the observation and the value returned from the function is lambda, right? So epsilon I in that case will have to assume the value lambda, right? And now let's suppose the epsilon I has some distribution, some probability distribution function p with mean 0, right? So what is the probability that epsilon I will hold the value lambda? So that would be p of epsilon I equal to lambda, right? So in a nutshell, if you have access to the function and some parameter w, right, which we think is truly explains the data, so in that case, we are given an xi, we compute its functional output, right, and this is y hat, and from the data we have an observation yi, right? So this function returns y hat, whereas in data we observe the value yi, right? So the difference is lambda, right? And we assume that the yi is generated by fw of phi of xi plus epsilon I. So in that case, epsilon I will have to cover this lambda part. So the epsilon I will have to assume a value of lambda. So in that case, the probability of this observation that we observe a value y is directly proportional or exactly equal to the lambda I covering the discrepancy between, or the difference between the y hat and yi, which is lambda. So this is directly proportional or exactly equal to the probability of epsilon I being lambda. And that's why in this particular case, when yi is some function of your input xi plus some random noise with zero mean and some probability distribution function p, and these are IID, then probability of yi given xi and the parameterization w is simply the probability of epsilon I. So this equation we'll use now to further derive some set of solution, or to be exact, like the maximum likelihood estimate of the parameter W.